So what we have done is really just made a definition which in the case of a tree, so if X is a tree, this is distance between Z and XY. So the XY is path from X to Y. And the path, I mean here the shortest or reduced path from X to Y. So given a pair of points, you take the path and you look at the distance, and here distance is the minimum distance. Okay, it's the shortest point projection from X to Y. So in the case of a tree, it happens to be this, but this function formula makes perfect sense in general, and we always call it the Gromov product. Okay, and so finally, what is Gromov hyperbolicity in this sense? Well, Gromov hyperbolicity is, well, to define it, we'll fix a base point Z and look at some more points. Okay, so here is X, here is Y, and on a branch here is, let's say, W. But I'll draw another tree just to avoid overgeneralization from one example, Y. Okay, so now let's look at the Gromov product of X and W. Okay, so for a tree, well, the Gromov product of X and W based at Z is the shortest distance with the path between X and W and Z. So it's going to be this line. Okay, so now in this case what happens is, well, this nearest point happens in this case to lie on the line between X and Y, not on the line between Y and W. But it must lie, because of thin triangles, by looking at the triangle XWY, it must lie on the line, one of these two lines. Okay, in this case, of course, it could be even further away. Okay, so here the line between X and W is quite far away. But nevertheless, what you have in all situations is that this is greater than or equal to the minimum of the Gromov product between XY W and the YW with Z. Okay, so this lets one make the following definition. X is delta hyperbolic if for all X, Y, Z, W. What we do is, in the case of a tree, we have the absolute situation, but here we allow an error. Well, it should be greater than or equal to the minimum X, Y, Z and Y, W, Z minus delta.